Hello. So how are you guys? I think the coronavirus is almost over soon. Then we will have a lecture in person, hopefully. Otherwise, we may have this kind of lecture in this semester. Anyway, hopefully it will be over soon. So first thing I'm going to do is to explain the quiz I gave you before. It was like that. Here is a game, a coordination game. So this strategy name may be different from the quiz I gave you, but it doesn't matter. So here is a player 1, here is a player 2, this is 2-1, 1-2, I think, 0-0, 0-0. I'll be checking whether this is the same normal form game that I gave you as a quiz, okay? Okay, almost the same, but I mean the strategy names are different, so that I'm going to change the name. So instead of using CB, I'm going to use SC. S stands for Starbucks and C stands for Coffee Bean. Okay? So the question was find all equilibria, including pure strategy Nash equilibrium and also mixed strategy Nash equilibrium. I mean, one way to find the pure strategy Nash equilibrium is simple, because as you can expect, if a first player expects that second player is playing S, then the first player will choose this, and the second player is choosing C, then the first player will choose C. Likewise, and this will be two Nash equilibria. That's okay. But my question was that find all equilibria. The other one is to find a mixed strategy Nash equilibrium. So I'm going to explain that. Okay, what is the mixed strategy Nash equilibrium? A mixed strategy is that, for example, player 1 is like mixing, going to Starbucks and going to Coffee Bean. I mean, if the player 1 chose going to Starbucks, it means this player 1 just decide to go to Starbucks. If the player 1 chose C, it means this player will go to Coffee Bean. Just go, okay? However, think like this. If here is a dice, after rolling a dice, this player 1 decides if the number is odd, even, the number is even, then go to Starbucks. If the number is odd, then I'm going to Coffee Bean. So when this guy is playing this game, the player 1 will not know which place this player will go. Okay? The only thing the player 1 knows that the probability of going to Starbucks, because he swears that he will follow the result of rolling a dice. If the number from the rolling a dice is an even number, then the player 1 will go to Starbucks, and if that number is an odd number, then the player will go to Coffee Bean. That's it. Okay? So in this case, again, but before rolling a dice, he just knows that the probability of going to Starbucks, but doesn't know really which place is really the player 1 is going to. we represent that result. I mean, this strategy is kind of a half, because this is a 50% of realizing, and the other one is also 50% to be realized. So 50% of Starbucks and 50% of Coffee Bean. This is the strategy that player 1 can play. Okay? However, as you can expect, if this player is choosing a different machine, gives him or her a different number, a continuous number. So think about a machine. If you push a button here, then if you push the button here, then this machine will give you a number, or maybe S, with probability P, and C with probability 1 minus P. Okay? It can be possible. In this case, I mean, people receiving the result, player 1 will not know which strategy he will play. He won't know. But all he knows that the probability of choosing Starbucks is P. The probability of choosing Coffee Bean is 1 minus P. That is his strategy or her strategy. So actually, I mean, by mixing those two strategies, player 1 can choose any kind of, he can derive any kind of combinations of these two strategies as a mixed strategy. Okay? So if we consider mixed strategy again, I should put here another row here. So let's that implicitly, let's that probability P be a probability of playing S. That is the P. So that P should be in 0 to 1. It can be any number depending on the machine. Okay, machine's setting. So if you consider this kind of infinite cases of combinations, so actually there will be another possible strategy will be mixing of those two. PS plus 1 minus PC. This is a kind of mixed strategy. In that case, we can calculate the expected payoff. That is the payoff if you play that strategy. However, that strategy payoff as something expected payoff when you are playing those kind of strategy. Okay? Say differently, the possibility of choosing when the player 1 is choosing S, and C, if you are playing this strategy, the possible payoff is actually, 2 with probability P and 0 probability 1 minus P. So in this case, first player's payoff will be 2P plus 1 minus P times 0. So that is 0. Right? And also, player 1 will get 1 P plus 1 minus P times 0. So that is the expected payoffs. Now look at this. If the player 2 is playing C, if I'm playing PS plus 1 minus P times C, then my expected payoff This is an expected payoff, not a realized payoff. Realized payoff will be 2 or 0. I don't know. I only can expect people playing this game, people rolling a dice, people pushing the button. People start the game. Aside, when we are thinking about whole story, people playing the game, before playing the game, we usually use the term in Latin ex ante. Ex ante. No. Ex ante. I should check this spelling, but ex ante. Ex ante. Ex ante. Ex ante. I should check it. But anyway, we usually call the name ex ante. Ex ante means people playing the game. So people knowing the realized outcome. That is ex ante. Also, we have ex post. Ex post means after playing the game, after realize the game. That's a different. Before starting the game, ex ante, then is the player, this player's expected payout. Likewise, if the second player is playing C, then expected payout is 0 times P, 0 times 1 minus P. That is my expected payout. And in this case, 0 times P, 0 times 1 minus P. So 2 times 1 minus P. That is my expected payout. Okay? Now, think from the player 2. This is 2, not 1. Think from second player's perspective. From second player, okay, if this guy is mixing, okay, then this P and 2, 1 minus P will be my expected payout. So if the second player is selfish and rational, then I would think like that. If now second player's view, if first player, if this payout, if the first player is playing this mixed strategy, if I'm choosing S, then I'm going to get P. If I'm choosing C, I'm going to get 2 times 1 minus P as my expected payout. So, if the P is greater than or equal to 2, 1 minus P, so if this is greater than this, then second player will choose S. If this is greater than this, I'm going to choose S. Otherwise, I'm going to choose C. Okay? Going back to the pure strategy normal form game, in this case, when you try to find the pure strategy outcome, if you are playing S, player 1 will choose S. From the second player's view, if the first player is choosing S, because 1 is greater than 0, then the second player will choose S. But in this case, I don't know which one is bigger. It depends on the size of P. So when P is greater than 2 times 1 minus P, then I'm going to choose S. So if I reorganize that inequality, it should be P greater than or equal to 2 minus 2P. If I'm moving this term to the left-hand side, that is greater than 2 over 3. So if the probability is greater than What is the P? P is the probability of playing S. So if the probability of playing S is greater than 2 over 3, then player 2 will choose S. But think about it. The fact that the first player can mix the game implies that the second player also can mix the game. Okay? So let's say that let Q be a probability of playing S from the second player. So, for example, Q equals 1 implies second player will choose S. Okay? So, we can rewrite this. If the P is greater than 2 over 3, if the first player has the probability of playing S with its probability, with the fact that its probability of playing S is greater than 2 over 3, then second player will choose S. We can write that as this, Q equals 1. So from here, we can write a response function of the second player. From the second player, player 2 will choose S if P equal to greater than 2 or 3. Right? I mean, I'm rewriting this part as Q equals 1. If P less than 2 over 3, then we'll choose C, or Q equals 0. Because what Q equals 0 means the second player won't choose S with 100%, meaning that second player will choose C with 100%. So, or if P equals to 2 over 3, what it means, these pairs are the same together. So for player 2, no matter what strategy he or she is choosing, it's indifferent. What it means, indifference, different. Or Q can be any number. Any number in where? In 0 to 1. It can be any number in 0 to 1. Okay? That is what the second player can do. That is the best response function. If you remind what we have done when we tried to find the pure strategy Nash equilibrium, I mean, we did like that. Okay? From the second player, if, for example, first player 1 is choosing S, then if we are choosing S, I'm going to choose S, right? If player 2 is choosing C, then I'm going to C. We can come up with those kind of plan of second player. That is the best response for the second player. So if we look at this is exactly the same thing as this one. Only difference here is that player 2 is considering when the player 1 is mixing. So that is the player 2's best response. Now think about this case. Now think about the first player. I mean, from the first player's perspective, if first player acknowledge that second player can mix. So again, Q is the probability of playing S. So Q S times 1 minus Q C. That is a mixed strategy of the second player. So if this player is mixing those two, then the expected payoff of the first player is 2Q, because times 1 minus Q, this is 0. And here, Q. Okay? This is times, for example, this is Q times 0 plus 1 minus Q times 1. So 1 minus Q for the first player. Q times 0 plus 2, 1 minus Q. So 2, 1 minus Q. This is the expected payoffs when the second player is playing C. So now think about from the first player. First player will think that, okay, if we are playing a mixed strategy, then I'm going to compare and this. If 2Q is greater than 1 minus Q, I'm going to choose S. If 2Q is greater than 1 minus Q, then player 1 will choose S. But I can rewrite that because this part means if I'm moving minus Q to the left hand side, 3Q is greater than 1. Right? So what it means, Q is greater than 1/3. So if I'm rewriting this, if Q is greater than 1/3, then player 1 will choose S, but I can rewrite with using P. P will be 1. Right? Likewise, if Q is less than 1/3, then P equals 0. If Q equals 1/3, I don't care what kind of strategy player 1 is choosing. It means P can be any number in 0 to 1. It means P is in this interval. It can be any number in this interval. What is this? This is the first player best response function. This is the second player best response function. Okay? When I find pure strategy Nash equilibrium, it was also same. This is the second player Nash equilibrium. Likewise, the first player best response I can write in this sense. Right? And then we can find some Nash equilibrium where they don't have any incentive to deviate from that current Nash equilibrium. Likewise, we can find the Nash equilibrium here. I'm going to use this area again, so I'm going to erase that part. So think about this graph. This is a P, this is Q. They can be in 0 to 1 and 0 to 1. So we can think about this rectangle. Think about this point. this point is where P equals 1, Q equals 1. It means P equals 1 means player 1 is playing S. Q equals 1 means player 2 is playing S. So actually this point represents they are playing this cell, this outcome. Likewise, this is P equals 1, Q equals 0, meaning that player 1 is playing C, player 2 is playing S. So SC, this point represented this cell, this outcome. Likewise, every point here, these 4 points, matches a pure strategy outcome. And this any point here is somewhere, some point which they are mixing those two strategies. Now from here, we can find the Nash equilibrium. Okay, player 2 said that if a player 1 is greater than, P is greater than 2 over 3. P is greater than here, player 2 will choose S, or Q equals 1. Q equals 1 when P is greater than 2 or 3. When P less than 2 or 3, Q equals 0. When P equals 2 or 3, then Q will be any number 0 to 1. So if I'm connecting this point, this will be first player's best response. No. Second player best response. Likewise, I can draw first player best response. First player said that if Q greater than 1/3, here this is 1/3, if Q is greater than 1/3, player 1 will play 1, P equals 1. If Q is less than 1/3, then P equals 1. If the Q equals 1/3, P can be any number from 0 to 1. Okay? So from here, what can we see? We can see that 3 points. In 3 points, their best response meet. Think about the point C. Point C, what is the best response? Best response, if you are playing this, I'm going to play this. If you are playing this, I'm going to play this. If you are playing S, I'm going to play S. If you are playing S, I'm going to play S. That is what these best response functions are talking about. So then where those two best response functions meet is a Nash equilibrium. In particular, this is a pure strategy Nash equilibrium. Pure strategy Nash equilibrium. Here, this. So this point represents this point. And point A, in the same sense, that is also Nash equilibrium where those two best response functions meet. Where this point represents this. This pure strategy Nash equilibrium is, representing where those two best response functions meet here. Also, we can find all of the best response functions, all the point where best response function meet. This point means 2 over 3 P is 2 over 3 S plus 1 over 3 C times Q. Q is 1 over 3. So 1 over 3 S plus 2 over 3 C. this point represents this. And I claim that that is also Nash equilibrium. In particular, this is a mixed strategy Nash equilibrium. Okay, this is a mixed strategy Nash equilibrium. Why? Because the best response function, a meeting. If we are applying this, if we are applying 2/3 S plus 1/3 C, then if we are applying 3/2, I don't care. 3/2, Q can be any number. So I don't have any reason to deviate current Nash equilibrium. If we are playing, this is Q, right? Q. If we are playing 1/3, first player can choose any number. So first player doesn't have any reason to deviate from current Nash equilibrium. If we are deviating just a little, it doesn't have any reason. So that, as you can see, in the middle of these two, somewhere, this is a mixed strategy Nash equilibrium. So that there are three Nash equilibria. Two comes from pure strategy Nash equilibrium, and here one comes from a mixed strategy Nash equilibrium. What it means? Okay, I don't know where you're going. So that I'm going to mix those two. But I'm going to give more weight of applying S, because when playing S, it will give me more payout. So I prefer playing S. But for the second player, she or he is going to play C more, because when she's playing C, she is getting more payout. It can expect more payout, so that she has more weight playing C. It is just representing their current circumstance. However, anyway, when they don't know where they are going at the end of the day, one mixed strategy is just mixing those two strategies. So we can find three equilibria. I hope you should understand the stories here and how can find this. It will be very helping for you to understand the gist of this normal form game. So I'm stopping here.